Yeah, thank you. And I'm really excited to be at Fields. I think I've last at Fields like 5 years ago. I was an undergrad, actually. So it's nice to be back in Canada and talking. And well, thanks for the organizers for sending me money to come up here. Well, I guess you haven't promising to send me money, I guess I should say. But that's right. Yeah, so this is the, I think the second or third iteration of the talk. And a major flaw in the previous iterations was that I don't think I actually used the word Wreath product after the title. So I have fixed that. So people who have seen an iteration of this before, it's been improved. Okay, yeah. Okay, so actually, I don't know if I should be happy or upset with Changing because he talked a little bit about Primeness this morning. But I'm going to give more history than he was able to write on the board because I have the advantage of just clicking instead of writing. Talk a little bit about factors and get warmed up with some kind of dynamic stuff. And then we'll get more into the meat and talk about, actually, we'll be more talking about property not gamma, and kind of rigidity and some representations related to that. And then we'll get into some results at the end. Okay. Okay, so, okay, good, I did fix. Actually, like an hour ago, it said no minimal projections. And I was like, oh, that's not a good start. All right, so type 1 factor is just a von Neumann algebra with trivial center and minimal projections, right? So our B of H. And if we have a factor that's not type 1, we call it prime if you can't split it into a tensor product. Okay, so like Changing said. You can actually also define this for non-factors. But we're going to stick to the case of factors because, at least in principle, you can use the integral decomposition to study non-factors. I say in principle because I'm a little traumatized currently from direct integrals, so I don't want to think about them too much. And the other thing is that, I mean, when you're dealing with prime, you kind of, you assume something is not prime and then try to derive some kind of contradiction. And you have all kinds of commutants lying around, right? I mean, if you have two tensor factors, then the commutant of one is the other. Okay, so having factoriality is going to allow, computing all these relative commutants just make it a lot easier. And then also, this first remark, I think Units actually made at the start of the conference, but we also exclude type 1 just because we always have matrix algebras lying around as tensor factors. So in the 2-1 factor case, you have all n by n matrices. And then in 2 infinity and 3, you actually have like a full copy of B of H. So it's, yeah. So you just say, okay, well, those are trivial. I mean, the primality question for matrices is just number theory, right? So we don't care. Yeah, it's like literally just whether the size of the matrix is prime. And the last comment is a bit more technical. So McDuff factors, so those with non-commuting central sequences, are not primed by McDuff's 1970 result because they absorb the hyperfinite factor tensorially. So if you have non-commuting central sequences and you're M, then M tensor R is M again. So actually R is an example of such a thing. R tensor R is isomorphic to R. So basically you want to avoid this scenario most of the time. Okay, so now you know what primeness is. I'm going to write it on the board to indicate that I've said what primeness is. Okay, so some history. So like Chang said, I mean, well, operator rings, so von Neumann algebras were introduced in the 30s, but the first primeness result, which is, I think, a fairly natural structural property, didn't come until 86 when Pope approved that, yeah, the free group factor on uncountably many generators is prime. So I mean, this is, yeah, a non-separable 2-1 factor. And so then in the late 90s, Go proved that, okay, well, there are separable examples, at least the free group factors are prime. And again, like Cheney said, yes, they're solid. Okay, Taka proved that hyperbolic ICC groups keep solid group von Neumann algebras and hence prime, as long as they're non-amenable, but this is like a relatively easy condition to satisfy. Jesse Peterson in 06, as a result, L gamma is prime if gamma has positive first L2 Betty number. And to my understanding, I think this might be the first example of at least potentially non-solid prime factors. Okay, but it's not trivial, but anyway. And then like Chang was talking about earlier, so biexact, at least for von Neumann algebras, implies solidity, but the converse is false, again, at the von Neumann algebraic level. And I guess I kind of think of all these results, and there's more in between. They're very like group theoretic, right? I mean, they're all, last one is not literally group theoretic, but it's inspired at least by group theory. So it's like, okay, well, these are all examples of when L gamma is prime. So I want to give some examples of cross products. So B to the gamma cross gamma. So this is the Bernoulli cross product or the just Wreath product. So Popa showed that if B is a tracial amenable von Neumann algebra and non-trivial, so it can't just be C, but it can literally be like C direct sum C, then it's prime whenever gamma is non-amenable. And actually, so I wanted to give a shout out too to my academic older sibling, Daniel Drimbe. So he actually proved that there exist cross products that even have property gamma. So this is somehow getting pretty close to being McDuff, right? So McDuff, I said, has non-commuting central sequences. Gamma means you have central sequences. So necessarily these central sequences are all going to commute. But he's still able to prove primeness for pretty specific types of groups and group actions, but still. And he actually proved more than this. He actually proved a prime decomposition theorem related to this. And then he saw in Maracci 19, expanded upon this 06 Popa result. So these Bernoulli cross products are prime, but there's basically no assumption on the base anymore, as long as it's non-trivial. So they prove it for the type 2 and type 3 setting. And this is actually very easy to see that a lot of these aren't solid, because if B is non-amenable, then its commuton definitely contains all of the other copies of B, which is not going to be amenable. So as long as B is diffuse and non-amenable, then it's definitely not solid. Okay, so I came back here because I want to kind of point out the outline for the next little bit of the talk. So one, we want to stick to the case of factors. Okay, so factors. And I also want to stick to, I want to avoid McDuff factors. By only considering things that don't have gamma. So that's a little bit stronger than technically you'd need, but it's going to make our lives a little bit easier. Well, for a couple of reasons. I mean, property gamma is much more well understood, I think, than McDuff or not McDuff. And we're going to have some bi-module theoretic results related to gamma that are going to really help us out. Okay. So let's start with talking about factors. This is our warm-up. Okay. So a 2-1 factor, we all know, is an infinite dimensional tracial factor. And it's separable if it's on a separable Hilbert space. If you have an action of a discrete group on a tracial von Neumann algebra, you can form the cross product. It's like the reduced cross product, but you take the WT closure. So I'm just asserting additionally here that if B is tracial, that the action should preserve the trace. So it's like 2-norm continuous. That's basically what I'm asserting. Okay, well, maybe something slightly stronger, but I want everything, I want it all to play nice with the trace, and then the fact that it's trace preserving is going to give you a nice, well-behaved trace on the cross product at the end. Okay. Now, if I is just a set, so I is just going to be an index set throughout the rest of the talk. If gamma acts on your index set I, well, what you can do is you can take some von Neumann algebra B, raise it to the infinite tensor product indexed by I, and you can permute the tensors according to gamma. Now, I guess technically that only defines an action on the so-called, I guess, pure tensors, the things that are, B1, tensor B2, tensor B3 inside of the tensor product. But this extends linearly because you can form a basis of tensors like this, and you can use continuity to define on everything. And then, okay, so you take the cross product of B to the I cross gamma. This is called a generalized Wreath product. So it's a Wreath product because you do the product and then act on it. And it's generalized because the index set is not just gamma itself. Right. So I've explained the title. I succeeded. All right, so we have, so basically the rest of the talk we're studying this algebra. Okay, so let's do a little bit of maybe dynamics, some exercises, and see how do we actually make sure we get a 2-1 factor? Well, we're gonna need a couple things, right? I mean, I said a 2-1 factor has a trace, so I mean, B should have a trace. I should have written really 2-1 factor. So I want B tracial. And I think basically, as long as anything here is infinite, then it'll be infinite dimensional. So that's not really a, I'm not even going to write that down. Okay, so first, you want the action to be properly outer on the space. So B to the I, I'm going to call this the spatial part of the cross product. And then L gamma lives inside the cross product as well. That's going to be the group-like part. So somehow they're like, you're almost always in the cross product, you're either doing something very group-like or very space-like. So, okay, so anyway, I want the action to be properly outer. So really I'm asking for the group to act freely in the kind of ergodic theory sense. Yep, so if B is diffuse, so if it has no atoms, then all you need is for the action to be faithful. If B has atoms, then you have to be a little bit more careful. You actually need each non-trivial group element to move infinitely many indices, which I call in my paper free, which I think a lot of people got upset because it's not exactly what free usually means. But it's called free because that property on the index set guarantees freeness on the Bernoulli action. So I think for most of the results, it's going to be, I'm just going to say B is diffuse, so I don't have to say free and upset people. So I'll say B diffuse, and but I can also just have the action be free, okay, in this kind of weird discrete sense. Okay, what else do we need? Well, we need the action. So actually, the first condition, what does that assert? It just asserts that the center of the cross product is going to be contained in the spatial part. That's what the freeness gives you. And so the rest is you need that you can't have a center in the spatial part. And for that, you need the action to be ergodic, at least on the center of the space. So it's sufficient to have infinite orbits. It's actually basically necessary. So I think the necessary comes in whenever the center is non-trivial. I mean, you could have B be a factor or something. So it's not necessary for factoriality in that specific case. But I want to take B to be just kind of a general object. I want to leave B alone as much as possible. And this is, I think, pretty believable, but it's really, really, really important actually to like basically every single argument related to these cross products is that infinite orbits is the same thing as like a weak mixing property on the index set. So every finite set gets moved away from itself by at least some group element. Yes? No, so these like together give you a 2-1 factor. So yeah, so for 2-1, basically all you need is B to be tracial, and the cross product will have a trace. And the fact that it's type 2 is just an infinite dimensional thing for us. So yeah, B being tracial is all actually, so this is for 2-1. And then either of these two things plus, see, I made this too close together. Okay. Yeah, infinite orbits. I guess you have to pick this one. It's like a weird menu, okay? You have to pick this one and then one of these two, and you get a factor. Okay, yeah. Yeah, thanks, good question. Yes. Okay. Yeah, so the factoriality is like the tricky part, yeah. Yeah, just having the trace basically gives you 2-1 for free. Okay, yeah, so they're together sufficient. So by the two conditions, I mean have a properly outer action and an ergodic action. You get factoriality. And I know I said it may be a kind of non-standard way or presented in kind of a weird way here, but I wanted to make the point that you can basically just assert actions only on the action on the index set and then get guaranteed properties for the cross product. So if I just assume that the okay, I need B to be tracial and maybe diffuse, so I'm trying to limit the assumptions there as much as possible. But if I assert that the action moves around a whole bunch of indices and has infinite orbits, then I get factoriality. So I'm really just saying, like, I only want to look at the index action and then deduce properties. Ideally, I like to be able to deduce like primeness from just some kind of property or set of properties for the indexed action. So actually, I want to kind of remind you of this Popa and Isono-Maracci result, which was instead of I here, we had gamma, the Bernoulli action. And they were able to prove primeness just as a property of the group, just because it's a non-amenable group. So I'm kind of trying to imitate that setup by saying, okay, well, list some fairly general properties for this index action and get, well, hopefully primeness. But we're not at that chapter in the story yet. Okay. I also want to say, I mean, this is, it's a little bit complicated, but it's definitely easier than like groupoid C-star algebras. So, this was known before 2021. Okay, so at least chronologically, it's easier. That's my argument. There's other measures of easier also, but okay. Oh yeah, and I added some. So this is a multimedia presentation. So we have chalk, slides, and colors. So that's 2 more than most people, I think. Not to brag. But the first condition. So basically, when we get to the end of the talk, so I want you to do this word association. Okay, so when we get to the end of the talk, and I start stating results, there's going to be all these adjectives in the statements. So I want you to remember, okay, diffuse and faithful go together, and they're going to give you freeness. That's really what it is. Okay, atoms are like a lack of diffuseness, and free, again, that just means freeness. So free means free, that's good. Diffuse and faithful means free. And infinite orbits means ergodic. Okay, they're all the same thing. Okay. Yes, and they're in color, so you can like more easily visualize them for longer. At least that's my psych theory. All right. Okay. Okay. All right. Let's get into property gamma. So I'm going to give a very non-standard definition of property gamma because I don't want to, because it's more fun to do it this way. I think it's the main reason. Okay. Actually, I'm going to write non-gamma here preemptively. Just making sure I'm not missing anything too crazy. Okay. Okay, so if I have 2, so for the purposes of this, I'm not actually going to assume too much knowledge about bimodules. You can just pretend that they're representations, okay? And they're reps for 2-1 factors, okay, for our purposes. So this precedes notation indicates weak containment, and that's the analogy of weak containment for representations. So not, it's a good analogy. So here's I guess 2 sets of theorems that you can take as definitions for the next 40 minutes. I'm not saying they're good as definitions, but at least they're true. Okay, so M as a 2-1 factor has property T if and only if the trivial being weakly contained in any bimodule implies actual containment of the trivial representation. This is like saying that the trivial bimodule is isolated in the space of bimodules. Or in other words, if you're thinking about representations, L2 of M is like the trivial representation. So it's like if you have almost invariant vectors, then you have invariant vectors. Okay. And then there's a nice characterization of property gamma, which I think, or it comes up in, or it's proved in this Ban and Maracci-Ozawa paper of 2019. M is non-gamma if and only if bimodules that are weakly equivalent to trivial contain the trivial bimodule. Okay, so this is kind of strange. So I think weakly containing the trivial kind of makes sense. Like you have almost central vectors, but this being weakly contained in trivial is kind of a weird property. So I think that's maybe something that people haven't thought about as much. So we have to justify why this is like actually useful, which is the plan. So property T is nice because the trivial is isolated, and so there's like kind of very little you can do with a property T subalgebra. You can kind of conjugate it around a little bit, but it really basically stays in place. And we was just talking about even if you have property T and a diffuse center, you still have like very strong rigidity results. So property T gives you a lot. The issue for us is that these generalized Wreath products basically never, it's not literally true, but basically never have property T. So that's like too much to ask for. We can't really use property T to do anything in very much generality at all. But we can definitely use non-gamma. Well, again, I'm going to justify why we can use non-gamma. And I'm also good. So, moral of the story: gammas are knockoff T. Okay, so it's like, Mom, can we go get property T? She says, no, we have property T at home, and then it's non-gamma. Okay, it's like, well, great. But it'll give us enough nourishment for the day. And both these properties are actually related, at least very slightly, to primeness because they are inherited by tensorand. So if you have a tensor product, the tensor product has T or is non-gamma if and only if the two tensor factors are, and vice versa. Okay. All right. Okay, so this theme of I want to say kind of as little as possible at the base, the spatial part, and really just use the group action to get properties, okay, that are going to hopefully lead to primeness. So this is the question, and unlike a lot of headlines when they ask the question, the answer here is actually yes, or basically yes. So for me, stab F is going to be stable. It's going to be, so you have a subset of your index set, all the group elements that fix every point in F. Actually, doesn't really matter if it just fixes the set, because it's a finite index inclusion. All of these methods are not really going to see finite index inclusions anyway. But just so everyone's on the same page, that's what stab F is. And this is not the W property, this is the VV property. So gamma acting on I has a VV property if whenever you take a central sequence in L gamma that is asymptotically in all the stabilizer subalgebras, then it's actually an asymptotically trivial sequence. So I want to point out, I mean, this is obviously a very kind of operator algebraic definition, right? I mean, there's an L gamma, there's conditional expectations, central sequence. This is not like a very group theorist property. It's a very like operator algebraist property. However, it is still a property of just the action on the index set. There's no B anywhere. It's just gamma and I. That's it. So a couple of examples of actions that do have the VV property. So actually, if you have any non-interamenable group acting on some index set, it'll have this property just because it doesn't have any non-trivial central sequences. So it kind of trivially satisfies the property. And the second one is if these are not exhaustive. Okay, you can have things that have VV that are neither of these. Or at least that's probably true. If the stabilizer of some finite set is trivial, and the action also has the VV property, so why is that? Well, basically you can take the intersection of finitely many of these stabilizers. And all the conditional expectations form a commuting square, so you can take the intersection of the algebras and the expectation onto the scalars, right? That's the span of the identity element. That's the trace, right? So that's how you would get that. Okay, so then the theorem. So why is this property interesting? Well, if you have a non-immutable action, I guess I didn't define what that means for these guys, but it's just the action on L infinity of I should have a left invariant mean. So it's the same definition as for immutability, except you change the set that's getting acted on from gamma to I. Anyway, but if you have a non-immutable action, then the VV property is equivalent to the cross product not having gamma. And I guess I have to add a caveat. It should be for B non-trivial, so it can't be C. I think that's the only caveat, though. So this is actually basically, if I just add in non-amenable and VV, so I could add non-amenable and non-interamenable, that'd be sufficient also. Then I get non-gamma. Okay, so I want the action to be non-amenable and I'll say, okay, this can either be okay, sorry, my brain's getting really small now. It's not good. Okay, non-interamenable or a trivial stabilizer. Okay. But I think that basically achieved the goal for this, okay? We got like non-gamma just from the group action. And by we, I mean they did. Okay, thanks. All right, so remember we had our knockoff property T, and so I said, okay, you have to have weakly equivalent to the trivial bimodule. And actually the weakly contained in the trivial being weakly contained in H is not really the issue. We actually get that out of kind of standard deformation rigidity type arguments. The trick is the other side. This is the weirder bit. So this definition, and by we, I don't mean me. I was trying to think of language to make it clear this is not my definition. This property is first described in that same Bannon-Maracci-Ozawa paper. And then it was named this in Isono and Maracci's paper. So again, you don't really need to know exactly what this is in terms of like, okay, well, I don't know what are the angle brackets. For those who know the jargon, this is the L2 space of the Jones basic construction of the inclusion P and M. But the point is that these are like very common and commonly arising bimodules. Okay, so this is like if there's lots of P's that are weakly bicentralized, that gives you lots of bimodules that we could potentially use to work with non-gamma. Okay, so let's gather some results about this. So the first proposition justifies the name. So this is hard to read, but I think it's hard for me to read out loud, but it's maybe easier for you to read the proposition. If the commutant of P and M omega is P, then P is weakly bicentralized. So you get these, so if you have this weak bicentralization, then you actually get this bimodule property, which we can use for a rep or bimodule calculations. And so easy consequence is that, okay, if you have actual bicentralization, then it's weakly bicentralized. So it's a reasonable name. Actually, to my knowledge, I can be corrected if I'm wrong. The proposition is an if and only if, not the in particular part, but the original part. So, sorry, let me restart. To my knowledge, the converse of the proposition is open. So I think it's unknown whether weakly bicentralized, in this bimodule sense, implies this relative bicommutant condition. And for those who don't work with, relative commutants all the time, this is different than the von Neumann bicommutant theorem because M is not B of H. Okay, so this is actually a non-trivial statement, which I have to remind myself all the time because I love the bicommutant theorem so much. This is not it. Anyway, this is my my knockoff von Neumann bicommutant theorem. I don't know if knockoff's the right word because it's like more interesting, or maybe equally as interesting. Anyway, so proposition. So this property is transitive. So if A is weakly bicentralized in B and B in C, then A and C. It's preserved under tensor products. Basically, it plays nicely with tensor products. The point 3 is 95% true. So the center is weakly bicentralized in M, but I think there's an exception if you have a non-separable type 3 von Neumann algebra. But we're in the type 2 one setting, so it's fine and separable. And the last one, I don't know if it's actually explicitly stated in the paper, but it follows from one of the propositions. If you have a free action, in my sense, okay, so it's not free, but it's free, like it moves around lots of indices and has infinite orbits, then the space, okay, the whole spatial part, is weakly bicentralized in the entire cross product. Okay, and actually, the reason this works is because B to the I has a lot of central sequences. Basically, you can take tensors that have support kind of further and further along the tensor product, and they'll asymptotically commute with B. And so you get lots of elements in the ultra power that commute with B to the I. And you get enough that when you take the commutant again, you get back to the space. Okay, so this is great. So we have at least a couple examples. This isn't really robust enough to actually use non-gamma for our purposes. So here's a theorem. So basically what this is saying that for every finite subset of the index set, there's a corresponding, actually it's a few corresponding, but in particular this one is a corresponding subalgebra that's weakly bicentralized in the cross product. This is basically, and these, you have to trust me on this one a little bit. These are actually naturally arising subalgebras. It's, taken on faith, but they actually are. So there's a couple of caveats. So, okay, so I said faithful and diffuse. I remember faithful and diffuse, we use that for freeness. Okay, so freeness is important here, like we need a properly outer action. But actually the diffuseness of B is needed not just for properly outer, it's actually also needed in like some relative commutant calculations. So there's some technical issues if B is like finite dimensional in particular. So what's really upsetting basically is that you try to compute this double commutant without the algebra power, because that's, seems easier. But then you realize that if the stabilizer subgroup has property T, then actually adding the algebra power doesn't even help you. So that's, again, that's a bit of a, that's one of the weird property T things. So actually it, potentially having property actually hurt us in this case, which is kind of upsetting. Because, so often you think property is going to help you out, but not today. Okay. All right, so let's do a little summary of what we have so far. So we want to find prime generalized Wreath products. We can characterize being a 2-1 factor, not quite characterized, but have like pretty robust sufficient conditions. And then also we can have a non-gamma 2-1 factor if we have some pretty general conditions, I think, on the index action. Okay, so the question is this enough? Well, one of the things I learned at Waterloo is that if you have one example and it works, then it's probably true. Okay, so let's Bayesian update our odds. So first example, this works. Okay, so this cross product satisfies all the conditions. So gamma is non-amenable, so the action is non-amenable. Let's see, the stabilizer of every point is trivial, and so we have non-gamma. I'm assuming, okay, you have to add in B is tracial. B is tracial, then it's a 2-1, then it's 2-1. Has infinite orbits, because gamma is an infinite group, and it's going to be free because every single non-identity point moves around every single other point. Okay, so that's good. All right, so it's probably true. But then the second part of my teaching was, if 2 examples are true, then it's like definitely true. But unfortunately, the second example is false. Okay, so so it's actually not true. So okay, what do I mean by this? This example, the one that doesn't work, is the coproduct action. Okay, so this is it's like a way to join together, 2 Bernoulli actions. All right, so we have basically the way is, okay, what am I trying to say? You have 2 orbits, one that looks like gamma 1, one looks like gamma 2. Gamma, if you have a G1, G2 from gamma 1 times gamma 2, G1 acts on things in the gamma 1 orbit, but it does nothing to the gamma 2 orbit, and vice versa. The G2 acts on the gamma 1 orbit, but does nothing to does the opposite. Yeah, and then it decomposes into a tensor product, right? So it's not prime. And if B is tracial, and these are Bernoulli actions of non-amenable groups, then it has all these things. So actually, in this case, it's this is like the tensor decomposition, the prime decomposition, because each of those is prime. Or I should say it's a prime decomposition, because I didn't prove that's the only way. But okay, so what's the problem here? So basically, the issue is the stabilizers. Okay, so the nice thing about the genuine Bernoulli action is that there's no stabilizers. All the stabilizers are trivial. So like you get this very, very strong type of mixing property. But in this coproduct example, the stabilizer is very large, right? The stabilizer of the whole gamma 1 orbit is all of gamma 2. It's like a massive subgroup, relatively speaking. Okay, so my interpretation of this is that it doesn't mix stuff around enough. Okay, you have a tensor product. You think of like a von Neumann algebra acting on itself by conjugation by unitaries. One tensor factor can't mix the other, because if you conjugate by unitaries, by commutation of the tensor factors, you do nothing. So it's not mixing it at all. And that's what's happening here, right? The 2 pieces don't mix each other. Okay, so let's, again, do some classical mixing. All right, so if X is we should probably say non-trivial probability space, then gamma acting on the, that's the infinite Cartesian product indexed by I, so this is the generalized Bernoulli action. It's mixing, in the ergodic theory sense, exactly when the action on the index has finite stabilizers. This is probably too strong, right? Because I mean, the Bernoulli action has trivial stabilizers. So if you have a mixing action, it means that on each orbit, you're virtually a Bernoulli action. Okay, so actually the primeness is just going to follow essentially from the Sono-Maracci result. Okay, modulo some details. But, okay, what's the next kind of mixing you come across when you're reading? Probably weak mixing. Well, the issue is that all you need for this action to be weak mixing is infinite orbits, which is not helpful because that coproduct action is weak mixing. Okay? It's 2 orbits and they're both infinite. So how can we fix this? So we have to, okay, we have to fix this. So here's 2 suggestions how to fix this. So one, we could just assert that all the stabilizers are amenable. This would give us some sort of like co-amenability stuff. It'll give us lots of bimodules that weakly contain other stuff, and then we can use maybe non-gamma to deduce actual containment. But it's like amenable mixing. Okay. So it's definitely weaker than having finite stabilizers, but it's also definitely stronger than weak mixing. And the second property, so I think it's actually fairly natural, especially we love amenability. The second one is a little bit strange, I think, in my opinion. So I'm just saying there's some finite subset whose stabilizer is amenable. And I want you to keep in mind that these actions are not transitive or anything, right? So I mean, this could be just like a giant 1 billion element set sitting in only one orbit. Okay, so this is like kind of a funky condition. But I have a justification for why we would care. And I apologize because some of the notation I haven't introduced yet, so this is slightly out of order. But the justification is basically this. So if one of your tensor factors intertwines, I'm about to expand on that a little bit, but if it intertwines into b to the f cross stab f, then it actually intertwines into all of the L stab g's for all, as long as g is finite. Okay, so so then the second condition, I can say that, oh, one of the stab g's is amenable, so then p intertwines into something amenable. All right. Okay, so let me kind of do a bit of a spiel about deformation rigidity, because I want to sell my research area so myself and my peers can get more jobs and all that. All right, so here's the theorem / definition. So the following are equivalent. So one, there's not a net. In the separable cases, it can be a sequence. So a sequence of unitaries in A that even when you multiply on the left and right by something in M, you can multiply anything on the left and right, and then you have to expect onto B. That basically can't go to 0. And the second one is there's actually a homomorphism between 2 corners of A and B that is intertwined by a partial isometry that has a nice lives in nice relative commutons. So this this is, looks pretty pretty technical. But why is it so powerful? Well, a lot of the arguments go, okay, we'll assume that A doesn't intertwine into B. Then you get unitaries with this nice property. And by nice, I mean you can actually get your hands on it and start computing. Okay, you can start writing down like, oh, the expectation of this onto this is something, and you can do some estimates, probably some Cauchy-Schwarz at some point, and you get a contradiction. And then you get a contradiction, and you can say, well, there must have actually been a homomorphism intertwined by a partial isometry. Right? So you get kind of this local thing you can compute with the unitaries, and you get this somewhat more global property of how algebras live inside each other inside the larger ambient algebra. Okay, so a couple like fun facts. At least if you have factors, unitary conjugation and taking corners preserves this intertwining relation. Intertwining is not quite, it's like almost transitive, but not quite. You have to add a couple extra conditions or a couple extra details. But it is almost. For us, what's kind of particularly nice is that if you have 2 tensor factors that are diffuse, neither can intertwine into the other. Okay, so they're kind of like permanently separated in this view. Actually, same thing for a cross product. as long as they're both diffuse, the spatial part can't intertwine into the group part, and the group part can't intertwine into the spatial part. So they're kind of separated in a very fundamental way. So I mean, if you had some calculation that contradicted that, right, then you're going to get some very strong statement about your algebra. And also, it's also just generally helpful, not just for primeness, but this intertwining stuff works really well with both relative commutantes and normalizers, and also quasi-normalizers. Okay. All right, so I've explained the notation. So I'm saying that, okay, P, if it basically intertwines into something with finitely supported spatial part, then it also can intertwine, so it can be kind of conjugated by a partial isometry into any stabilizer you want. So this is kind of like, P living inside of B to the F cross tab F is kind of like, okay, if P already has $1 million, then actually it has $1 billion. I mean, it's it is a stronger statement, but it's maybe somehow getting to $1 million is really the, I don't know. That's the tricky part, in my opinion. Actually, they're both tricky, but they're of a different nature, let's say. Okay, and the last couple of slides, they're just basically just going to list results. Okay, so the top one is a technical result. So if you don't like intertwining, I did a bad cell job, you can just look at the bottom one. But the top one is kind of the meat. Okay, this is like how the proof actually goes. So if you have a faithful, non-immutable action with the VV property of a countable group on a countable set, diffuse traceable Neumann algebra. So we kind of just go through one of these adjectives to make sure we have a non-gamma 2-1 factor. And non-immutable actually implies infinite orbits. Okay, so I actually saved one word. Not very impressive, but that's okay. Okay, so we have the generalized Wreath product, right, as a tensor decomposition. Then I can say something about one of the tensor factors. Okay, so either it lives in all these stab Fs by the theorem that goes from finite spatial part to any stabilizer, or the other tensor factor lives inside one of these algebras. And if you remember, these algebras were the ones that non-gamma sees really easily. Right? These were the weakly bicentralized ones. Okay. And so I'm doing some bimodular calculations and looking at some relative commutantes. One corollary you can extract out of this is that if you have an action that's faithful with infinite orbits, acting on a 2-1 factor, or I guess a tensor product of a 2-1 factor, and have enough conditions to say that that M is actually non-gamma, and one of the stabilizers is amenable, then you get primeness. So just having one amenable stabilizer gives you just enough mixing to get primeness. Yeah, so I know it's kind of weird. Maybe I wrote non-gamma and then still have to write faithful in infinite orbits. The non-gamma part allows me to do all of the nice bimodule calculations. The faithful and infinite orbits allows me to do some other arguments later on. So I do need like the ergodicity and freeness in other places in the argument, actually, to do some of these like bootstrapping or weak bicentralization type arguments. And then something that I said, I went from B diffuse to B a 2-1 factor. Yeah, there's a relative commutant calculation at the end where you need a factor. Yes, this is like I said at the start, right? You need factors to do a lot of these commutant calculations. All right, now something else about this bottom result is that it doesn't actually directly generalize Isono-Meraki's result, even in the tracial case, because I'm saying BS be a 2-1 factor. Okay, like I'd like to say B is just non-trivial. But using similar techniques, I was able to extract a generalization using this amenably mixing. So if all the stabilizers are amenable, then you just need, and add in the right soup of adjectives, then you just need a non-trivial base. Okay, so like I said, this is like an actual generalization of the Popo-Isono-Meraki results. And then I put in kind of a group-like example. So if you have a non-amenable group and an amenable subgroup, where the amenable subgroup is malnormal, so that's what malnormal means. Intersection of finitely many conjugates is trivial. Then so the corresponding action is the natural action that's transitive, right? I mean, it's just gamma acting on the quotient sets, or the cosets. this thing will be prime. Okay. All right, and that's it. Thank you.